So we're ready to start.
Yeah.
And Brody will tell us about reinforcement learning and math theory.
Thanks. Can you guys hear me up the back okay? You guys hear me okay up there? Yeah? Okay. Cool. Okay, this lecture actually is just about reinforcement learning. There won't be any knot theory. So Fabian gave a lecture on Wednesday about reinforcement learning and knot theory. And but the first half was reinforcement learning, and that's what we're going to be focusing on. Just the basics of reinforcement learning, trying to look at the code behind some basic environments, some basic algorithm to train an agent. And then hopefully later on we'll get to some maybe slightly more interesting cases. So if you haven't already, please go to the school website. And this is the link that you're going to need to click here. It's again a Google Colab notebook. If this isn't showing up, you might need to do like a hard reset, a hard refresh of this page, which is like Control-Shift-R, I think. Or it's just the same link as this last time, but this one is a 2. Okay, so if you click through on that, then you should get through to the Google Colab page. Okay, so like I say, in this one maybe in particular, if you try to do it locally, you might run into some problems. So I'd try to do it on Google Colab. I'd say it would be much easier. Cool. Okay, so we're going to look at reinforcement learning, some of the basic concepts, and I'll be doing a bunch of basically review on the board, and then we'll be jumping back to here and doing some little exercises. And later on, we're going to look at some OpenAI gym environments like this lunar lander here, and we're going to grab from this library stable baselines some algorithms for reinforcement learning, which will train to land this lunar lander. Okay. So I'm going to start talking on the board, but these packages here, which you need to install, will take a few minutes. So if you can get them, if you can just run this cell now, so that by the time I finish talking, you've got everything ready, that'd be great. Yeah, and then I'll come around in a couple of minutes when I'm done with the blackboard to see if anyone's had any trouble. Okay, cool. So we're going to just review the basics of reinforcement learning because it's been a couple of days now anyway since you heard about it. So the basics are in reinforcement learning, we have some kind of environment, which is like a set of states and actions you can take within the environment. And you have an agent which can take actions on the environment, and it gets some kind of feedback in terms of a reward. And the goal is to try to train this agent to achieve the highest cumulative reward by trial and error. So in particular, we're going to look at a simple environment, a very simple environment, which I actually have over here. Yeah, so this little grid world, this is like a 5x5 grid, so I've drawn it on the board as well. And it's called a grid world because you can just move around on this grid. And in blue in the top left is a little worker that is going to be the guy who moves around. The red are pitfalls that if you fall into them, it's a bad thing. The green in the bottom right is the goal where you want your worker to get. And that will be a good thing. It's going to have a positive reward. Okay. Yeah, so the most basic thing we need to define for our environment is a state space, which is just a set of possible states. In this case, the only thing that can change is the worker. So as the worker moves around, there's a different state. So you have a discrete state space of 25 states. Nothing else can change, so it's just indexed by where the worker lives. So we have this, which is order 16, order 25 states. This is obviously a really simple case. This is just a discrete state space. You might have more complicated ones with a continuous state space. And you also might have obviously much more complicated states. It might be that the worker's here. There's a whole bunch of other guys on the board. So this is a very simple case. And we have some sort of like world initialization. We'll come to this when we look at the code for how to do this. We've initialized these bunch of pitfalls, and this endpoint. And these are terminal states. So if you step on one of these things, that ends the playthrough. And then the possible action states, so the action space for our little worker is just we can move up, down, left, and right. Yeah, we can move up, down, left, and right. There's 4. It's again discrete. The action space is discrete as well. And if you were sitting at, say, the corner or against one of these walls, you still have the same action space. But some of the actions, well, you could either treat it that if you step outside here, this is the terminal state and the game ends, or maybe you just get bumped back. So the actions are still possible, but maybe they have a different effect here against the wall. So the action space is the same. Okay, and then you also have a set of rewards, which are going to feed back to, as we move this worker around, which is what our agent will be trying to do. Depending on what it does, we're going to feed a reward back to the agent to say you did well, you did badly. So we have a set of these rewards. And reward you tend to write as this little r. And in general, it could depend on the state you're in, the action you take, and then the state you end up in. But sometimes you simplify this to say it's just, you might only assign a reward depending on the state you were in, the action you took, or maybe even just the state that you ended up in. Yeah. Usually the action is, yeah. I guess the full action space would be the same. But which ones are available would depend on the state. Yeah, so this would be the simplest kind of possible reward. Maybe here it would just be if you fall in the pit, bad. If you get to the goal, good. But as we'll see in a second, actually, in this case, there are some rewards which depend on the state and the action. These two types of reward sound the same because if you're in a state and you take an action, surely the state you end up in is fixed. But it might not be if, say, the environment has some stochasticity, that you try to do something but you can't, and so you end up in the wrong state. Something like that. But for this case, this kind of fully deterministic case, these should be, I think, equivalent, and these will be the kind of rewards that we have in this case. Okay. Yeah, so I said there's a positive reward for falling, positive reward for getting to the end, negative reward for falling in these pits. But there's two other types of reward. So I'm just going to get you guys for a couple of minutes just to get familiar with this. Just hopefully your packages have installed now. What you should need to do next is you should be able to import everything you need. This next code cell, which should only take a second. And then just to use this grid world, we're going to need to grab these couple of files, which is what this code cell does. And then actually, if you want to see that it has actually grabbed those files, you can open this little files tab on the left. Well, I've got a bit more, you shouldn't have this. But you'll have gridworld.py and helperfunctions.py. And then you can import these. And when we've done that, we can create this grid world. So this we'll look in a bit more detail at what this code is actually doing later, but we're creating this game environment, this grid world, and we're choosing a particular random seed because this grid world is created randomly. The pits get moved around randomly. So we're going to fix the same one, so we're always all working on the same one. So this will set up your environment env, and then if you run this, so you should be able to see a picture of it. And this is explaining the same stuff I've already said. And then if you want to move the worker around, there's a function, there's a method that you can run on the environment called step I, which takes values 0, 1, 2, and 3, which are, I've forgotten the order, but it's up, down, left, and right in some order. And so if you guys could just play around for a couple of minutes with getting this guy to step around and then revisualizing where it's ended up and checking what the different kind of rewards are that you get when you move around. So env.step will give you some returns. It tells you which state you ended up in, also which reward you got. And then there'll be, I think, a third return, which tells you whether you're done because you fell into one of these pits or you ended up at the goal. So if you guys could just play with that for a couple of minutes, and I'm just going to come around and see if anyone has had any trouble setting stuff up. Sorry? Yeah. That's what I'm asking you guys to do, but yeah, I can do that. Yeah, so if you want to do that, if you haven't already, do I need to remember this again? There. You can grab the same code, which was basically displaying the world. And I just need to step my guy. I don't know, I've forgotten which one 0, 1, and 2, and 3 is. Oh, sorry, the up, down, left, and right, that's the order. So let's try stepping down. Yeah, okay, so my guy moved down, that's great. And then I was saying, just try and move around, figure out what the reward is when you go into the pit, figure out what the reward is when you get to the maze. And like I said, there's 2 other rewards which you should see. And in particular, yeah, so let's have a look. Let's step down again. Yeah, so this kind of step guy, which we're going to see, is common to these environments. It's going to give you some sort of return. What is given here is the position you ended up at. I should probably say this is sort of, this state here is 0, 0, if you're wondering. The state here is 1, 0, and then down here is like 0, 1. So x increases this way and y increases down. Okay, so depending on how you're going, yeah, you should see that when you take a step, it returns where you are now, it returns the reward, that's what this second guy is, and it returns whether you're done, whether you fall into the pit or the maze. Those are the done cases, the terminal states. Okay, so depending on how you moved around, you should have found that there are 4 types of reward. One, if you fall into the pit, you get minus 50. Maybe I'll write this up actually, because you might need to. Pit, you get minus 50. If you get to the end, you get actually 100,000. Any step at all is penalized. You get a -1. And then if you run into a wall, you don't move, but you lose, you get a penalty of -2. So this is a kind of reward, which is like a reward that depends on the state and the action. Because if it was just a state, then it would just be the -1 again. Okay. But let's be a bit more specific then. Yeah. Okay. So an environment, when I say environment, and the kind of code that we'll look at for an environment, which will be this next part down here. There are really 2 parts to that. So one part is the actual environment itself, like the game world, like this. And the other part is basically how it can interact with an agent. So we'll have to specify both when we specify environment. So first of all, for the environment, what we need, as we said, is a state space. We also need some sort of way of initializing things. Maybe it's random, maybe these pitfalls move around every time. It also needs some kind of, basically some internal dynamics, right, that are going to run how the game world actually runs. So we're going to have to specify that. And that's going to depend a lot on the specific environment. And we're going to need a way to reset it after playthroughs, which might be different from the initialization because, for example, here we initialized all the pits, but when we reset, we're not going to move the pits again. We're just going to put the worker back. It'll be the same maze every time. Okay. We have this environment. And it has some like internal state, like internal dynamics, which are going to tell you how the states move back, how you transition between states as the agent takes actions, for example. And then we're also going to have an agent, which is the thing we're going to train later. And the way these things interact is I perform some action on the environment, and it returns to me an observation of what's happened. It returns a reward, and it returns whether you finished or not, whether the playthrough is finished. And all of this we'll see in a second. The standard way to put this as a method on your environment is to use dot step. So we'll see that in a second. Dot step will take an action on the environment, and then that will do all of this. It will return something for the agent. Okay. So this part here was the what's sort of going into the environment, what's going into the actual interaction with the agent. We need to have, okay, so we need an observation space. So far we talked about a state space, which is all the possible states that this internal game world could be in. There's 25 possible. When we hand information back, so when we perform an action on the environment, it updates the state. But what we pass back isn't necessarily the whole state, because some information might be hidden. Instead, you get some partial information, which is called an observation. And here, yeah. So if it was like a game where you can look around, then the observation would obviously just be the pixels that you see. We have some observation space that we need to define, which is analogous to the state space, but it might be some partial information. And then you need the action space, which we already mentioned, which is the set of things that the agent can do. And then, as we said, obviously we need, well, okay, no, so we need the effect of the actions. We need to know how those actually change the state. And we need, finally, the rewards, which we already talked about. Rewards for states, for actions. Okay, so let's look at how this actually works. Is there anything else I want to say? Yeah, okay. So the way so here I've talked about the states and I've talked about the worker here, but I haven't talked about how that agent is actually going to interact, except to say that the actions that we can take are we move this little worker around. What observations do we pass back? You saw if you were running this code that what you pass back as an observation is just the position you're at and how bad or good it was to do this. That 0, 2 is nothing like the whole maze. We're not passing back. We're just passing back the position you're in and whether it was good or bad. Actually, in this case, the observation space, there's also just 25 possibilities, so it's the same as the state space. But we're not passing back information about like where these guys are. We're just saying, here you are, and it was bad or it was good. So it's sort of, this guy's sort of moving around blindly, right? The observations are really partial. He's just living in a box and doesn't know what's going on. Okay, so let's look at the code behind this environment to see how these things are actually implemented. Or unless there are any questions before I do that? Okay. All right, so this game environment, the grid world, is just, we set it up as a Python class game env. If you're using an OpenAI gym environment, and we'll look at some of them in a second, and this is sort of a more standardized form, that might inherit from the gym.env class to make sure it has the same methods, but this one doesn't. And then, yeah, I said there are two parts: environment, the environment itself, and the interface with the agent. So the first part, this internal representation, is going to depend a lot on the game, on the case. So in this case, there's this piece of, if you go look at the code, I mean, you can look at the code yourself, it's not very long. It's in this files tab, obviously. But there's a part which just, it stores objects in this class game obj, which just, records the objects and what kind they are, what kind of reward they give if you fall on them, where they live, and this is something about visualizing it, which we're not going to care about. There's a bunch of code in this that's for visualizing the environment, which I'm going to skip over. There's some code to initialize the environment, which basically sets up the size, how many pits we want, where the little worker is going to start. And then when we initialize, we put the exit somewhere. We put it at 4, which is the bottom right. Give it the appropriate kind of reward. These things are about drawing it, so this is not actually important. And so we put that in the objects, the maze exit we put in this objects. The worker we put at the top left. And then we step through the number of pits and we put a bunch of pits in. At random, this is handling the random positions. Okay, and there's some internal dynamics, which is how this worker gets moved around. So this is basically the only thing that can happen. So here it's just, this is code that's grabbing the worker out of the objects, seeing where it is, and then it's starting off by saying, okay, the default reward is going to be -1, but then we're going to update it if we do something more interesting. And then here's where it tries to move. So if you try to move whatever this is down, then it's going to update the Y value. But this is checking if you're at a wall. or not. These extra conditions are like if you're at a wall, you can't move. Okay. And so if you weren't able to move, you get this extra penalty, no move penalty. Yeah, and this is just detecting where the worker is again. And then this is checking if you fell into something, so it steps through the exit. If you got there, then you get that you get a reward, negative reward. Sorry, positive reward because it's the exit. It tells you that you finished, and if you fell into a pit, it also is going to tell you that you finished because you fell. Okay, and as I said, in every one of these sort of gym environments, you're going to need a reset function. So the step function was the other really common one. That reset is the other thing that we're going to have that's in common, which is just resetting the environment. In this case, it's just going to put the worker up in the top left and keep track of whether it's fallen yet and so on. Okay, so the second part of the environment is how it interacts with or how the agent interacts with the environment. So we set up, as we said, an action space, which is just a discrete set of 4 possible actions. And the observation space, as I said, in this case, actually just coincides with the state space. It's just the 25 possible positions. So here, it isn't even distinguished between, when you perform a step, you actually just return the state. But in general, this would return a partial observation. And it is partial in the sense that we don't know where the pits are, but it's the same as the state. Yeah, where state just tells you where the worker is. So in this particular case, when you act with the agent's actions completely fix the state because it just moves the worker and that's it. In general, that's not going to be true. Obviously, there could be more complicated stuff. The observations are the complete state, which is not going to be true in general. And here we sort of identify an agent with like some guy that's living inside the environment, this sort of worker. But in general, that won't be true. Maybe the agent sits outside the environment, controls multiple parts. Okay. In OpenAI gym environments, which we'll come to in a second, you specify an observation space and action space with this syntax. This is a spaces is a class, is a superclass in OpenAI that has discrete spaces. It also has box spaces for continuous cases. So this is, in our case, discrete 4 and discrete 4. And you can go and look here if you want to find out the other sets of options. And then when we take an action, so the other part that's really common is the step method. So, we pass it an action and it moves the worker, which is like the internal dynamics part of the environment. It also keeps track of what kind of reward we should be getting based on this. Yeah, and it returns, as I said, the state, the reward, and whether it's done. And finally, we need to actually set up the rewards, which are here. So this is a reasonably common kind of environment. And if you want to look more at it, you can click through into the files and have a look at it. Are there any questions on this before we move on a bit? No? Okay. So I want to talk then a little bit. So we just talked, yeah. So I want to talk a bit about trajectories, returns, and policies. So we've talked about how you can move to a place, you get a reward or not. But the full set of actions you take and the rewards you get is called a trajectory, or an episode. So an episode or a trajectory, tau, is set of state, action, and so on. And you do need to, in this totally deterministic case, maybe it'll be enough to just keep. Actually, if you hit a wall, you'll need the action. We have to keep track of states and actions. So, for example, some example trajectory. Maybe we start here, we try to go down, we come up because we bounced against the wall. We move over here, and then we move up here and we fall in a pit. Cool. Okay. Now, so I next want to define the return, which is a function of the trajectory, which is basically the rewards you get, summed up as you go. But they come with a discount factor, gamma. So this gamma could be something like 0.9. And it means that as you take more and more steps, I'll just write this actually. I know I want. The future rewards that you get are discounted more and more. And mathematically, this is nice because under certain conditions, at least, this will converge. But also intuitively, it makes sense because maybe you should be less sure about returns, about rewards that you're going to get in the future because maybe something goes wrong between now and then. So yeah, so we have discount factors. This could be any. This could be. It depends on your problem. It could be 0.99. It could be 0.9. Whatever. In this case, I'll make it 0.9. So for example, for this trajectory, the return would be -2 because we hit a wall, and then 0.9 times -1 because we take a step, and then 0.9 squared times -50, which is -43.4. Okay. So now a policy. Okay, so that was return, that was episode, and then the final thing is the policy. Any questions though on returns or anything? Returns or episodes? Okay. The policy is a way of choosing actions given a state you're in. If you're here, your policy might tell you to go up or to the left or whatever. Okay, yeah. So for example, let me draw a concrete example of policy. Maybe you're here and you go down. You're here and you go right. That would be a bad policy, but it's a policy nonetheless. You go up and whatever. And there are deterministic policies, which is, how should I say this? Yeah, you might decide to build some randomness. It might be that if you're in a state, you sample from a probability distribution of what kind of states you want to, what kind of actions you want to take. But here I'll think about deterministic ones. Okay. Well, policy you tend to write. Sometimes people write mu for a deterministic one and pi for a stochastic one. I think pi is a bit more common, so I'll just write pi. Okay. Now we have a notion of a goal that we want to train our agent towards, which is we want to find a policy which maximizes the return for any trajectory. So for example, obviously this wouldn't maximize the return because this would be stupid. If you started here, you just go straight in here. There's some more optimal policy which is actually learned to satisfy this, to meet this goal would be trying to point us towards the exit. So yeah, if from every point you can find your policy directs you along the trajectory with maximum return, then you have what's called an optimal policy, and so that's what you're trying to train for. Okay. Okay, so just a quick exercise then to try to make sure for yourself that you understand these concepts. If you could just figure out what the optimal action is at a few different points, including, for example, up here, these 3 points up here. And then, yeah, as it says here, compute the return if you act optimally from the start point. If you act optimally from the start point, but you take a step backwards at some point and then keep going, which would not be in total would not be optimal. And yeah, if you acted optimally from up here, what would be your return? The 2, 0 is this top middle point. So I guess you can just chuck that in mathematically really quickly and try to get compute this just to see that you actually get the right numbers. And I'll write the numbers up in just a second. And obviously, in this case, an optimal policy is kind of simple. You just want to get to. It might be more complicated if, for example, there was like coins down here that could give you some kind of reward. Maybe you want to get the coins first and then go to the goal. But if you're here, you just want to get to the exit quickly. So it could be much more complicated. But in this case, the optimal policy should be pretty simple. While people are doing that, has anyone had any problems getting anything set up? It might seem slightly boring, obviously, to just like compute these returns, but they're going to be crucial when we come to the next thing we're going to do, which is going to be value functions, which actually is what we're going to train our agent to learn, at least in this simple case that I'll present. Okay, all right, maybe that's enough time. Yeah, so the optimal action, obviously, if you're anywhere down here, you just want to get to the goal as quickly as possible. So like this will be optimal action. Here you could do either. Either would be optimal. Here you should go down and so on. Here it's pretty simple. If you're up here, any action could either put you straight in the pit, which is very bad, or it could just move you up into one of these other steps, which would be the least bad you can do. If you bump into a wall, that's worse. I think the optimal policy here would just be to bounce yourself around. In this case, we're never going to be there because we end up here, but in principle. And then for the three questions, for the three returns, I got 42.6, 32.6, and minus 10. If you're up here, the best you can do is a minus 10 return. If I got one wrong, let me know. Okay. Anyway, so now we can talk about something called value functions, which is a really crucial part of enforcement learning. So a value function, so there are three kinds. I'll start with V, and then there's a kind called, which is called a Q function, and then a part called an advantage function. The value function is just is a function of the state, and it's just the return that you will get from that state if you take a trajectory defined by your policy pi. So if you fix a policy, then every point has a certain value, because if you're going to act according to that policy, then it might be a bad state to be in or a good state to be in. And then there's an optimal form of the value function, which is V star, which is if you act according to like an optimal policy, let's say. So for example, on here, if you start here, then and you act according to an optimal policy, you'll just go straight down here, which will give you 100. Same here, so this will be 100 as well. If you start here and you act optimally, so you go here and here, then you get 89. Same here and here. So these would be the values of the value function, the optimal value function, and obviously others. Up here you get minus 10 and so on. And you computed this guy as well, maybe. So you would have got 42.6 for the value function up there. Okay. Then you have something called an action value function, which says, okay, if you're in this state and you take this action, and then after that, behave according to the policy, then what return would you get? Yeah, so similar, but you actually take an action first, you end up at another state. So this will be the reward you'll get at this state for taking this action, plus the return of acting. This guy starts at S prime and then goes on. And we're acting here according to a policy pi. You first get some reward for the first thing you do, and then you end up at another state and you act according to the policy after that. And then you also have an optimal one where you just take the policy to be the optimal policy. And then finally, you have an advantage function, which is just the difference. So it's basically saying, if you were to take this action and then act according to a policy, how much better would that be than if you just took the action from this state that you were already going to take? So this is like the return you'll get if you just start acting according to the policy now. This is the return you'll get if you take this step and then act according to the policy, which could be the same, and then these will be, if S is the same as, if A is the same as what your policy will pick, then this will be 0. But it's basically measuring if some action is better than what your policy currently says you should do. Right. By the way, if you're computing these things, yeah, I said in here, use 100 as the exit reward, not 100,000, just so the numbers are a bit better. That's why, maybe if you're confused and you got like 100,000, 100,000 is in the code because it's going to make it train better, but 100 is better for these numbers. And so, yeah, just quick exercise again. If you guys could compute these three value functions, the action value function, another action value function, this advantage function, see that you get the right numbers to see that you understand how these guys work. It'll just take 2 minutes to do that. Yeah, and so these points are here. This is Q3. So here I'm asking, if you start here and you go up, what's the Q function for that state action pair? 1, 4 is 1, and then it's here. So if you started here, and then you went down, and then acted optimally, what would you get? And then what was the next one I did? If you started here, and then you went up, this goes 3, 4. What would you get for the Q function? Sorry, that's an advantage function, not Q function. Okay, well, I'm not sure how many people actually computed that, but that's fine. The answers that you'll get, that you should get for those three are, I think, minus 50, I got 69.2, and I got minus 20.9. So this guy here being negative, obviously, this is an advantage function. This means that the action you took was a bad one. I mean, the policy that you would have been better off just following the policy, which in this case would have been, Did I make it clear that these are optimal value functions? Maybe I didn't. Obviously, you need a policy to compute a Q function or an advantage function or a value function. And I haven't specified a policy. So these were supposed to be the optimal, I guess I said it here, optimal value function. In this case, you should have moved right, and then you would have got a return of 100. But because you went up, right, down, you did worse by 20.9. Maybe. Yeah. Is it? Well, so it's clear that the value function is 100. So what do? We step up, which costs us -1. And then we step right, which costs us 0.9. The third one, I'm computing the advantage function. Sorry, yeah, right. I'm computing the Q function now to compare with the value. Sorry, this is not good. Sorry, this is not right. Because this should be the return. Yeah, sorry. So this was a mistake. There should be a gamma here, because the next guy will be penalized. Next step will already be penalized. Hopefully, with that, this was correct. Thanks. Okay. Okay. So, like I said, in a second, we're going to write down an algorithm that's going to allow our agent to actually train to do something. And we're going to do maybe the simplest algorithm. And so I need to do one more thing with value functions, even if maybe they seem boring. It's what your agent is going to learn on. So it's important. So we can define these Q functions. We can think of having a Q table. So for every action, so for every state, so we've got a whole bunch of states. We've got 16 states, which I'll put vertically here. Sorry, 25 states. Down to like this guy and this guy. So maybe we're going left to right. And then for each situation, for each state, you have an action you could take. And then the Q table is just filled with the Q values for those states' actions, for the policy that you're working on. So if I'm thinking about an optimal Q function, are there any questions, by the way? I saw a couple of people maybe look confused, but maybe not. Okay. This one? I might have just got it wrong if everyone else got a different answer. Okay. I might have got it wrong. Which one was the second one? It was starting. Yeah, so we start here. And then I run straight into the wall. Yep. Okay, so I did it in mathematics, so I can't do it in my head. Which number was this supposed to be? I actually have no idea how to do that. How do I do that? Oh, yeah. Okay, cool. All right, so what do we need to do? So we need to do -2 is the first thing that happens. And then gamma times, and then what do we need to do? So we just bumped into here, and then we took 1, 2, 3 steps, I guess. So we need this 3 times with different gammas. Yeah, I might have just got this wrong if people are getting a different one. Oh, that's terrible. Oh, sorry, I need to take. That agrees with that, but is this calculation not the right one? I think it was right. I bumped in, I lost -2. I lost -1 for a step, -1 for a step, and then 100, but they're getting discounted by the discount factor. Then I guess this last one actually was probably just no, okay, no, that's not right. Okay, so hopefully that is that clear then at least? No? Okay, cool, yeah. Okay. All right, yeah, I was talking about the Q table. But, if you went through and computed all of these values of the optimal of the Q function for the optimal policy, yeah, you would fill this table out completely. Example, this 3-4 case. If you just move right straight away, you get the full 100. This is 3-4. You get the full 100. If you moved left first, you can check. You get 79.1 in that case because you get you get a -1 for your first step, and then we don't need to recompute things. I guess this is the crucial point for what I'm about to say next. You don't need to recompute things because we already computed the value function for here. So I don't need to now go, here and then step back and back. I can go here, get my -1 reward, and then add gamma times the reward from there, which is 89. So that's how you get 79.1. If you go up, it's the same because you ended up at 89. So this would also be 79.1. If you went down, you bump into the wall, and you end up getting, you lose 2, and then you get 90. And then you'd have all the rest. Okay. So we would have this, in principle, there's this Q table, and if your agent could learn this optimal Q table for the optimal Q function, then you could have an optimal policy, right? Because it would just choose the move, it would just choose to take the best options, the values. It would choose the actions that give the highest Q value, and that would maximize its cumulative return. So if you can learn the Q table for your agent, then you've learned an optimal policy. So let's think, so this brings me to an example of a simple reinforcement learning algorithm. So the first thing maybe I'll say is there's multiple ways you might try to train your agent. And sometimes when people talk about reinforcement learning and say, it's this trial and error thing and you give it rewards and it learns, it can seem like maybe it should be clear how this thing learns based on the rewards, like it just learns immediately or something. But it's complete choice how you get your thing to actually learn based on these rewards. In particular, broadly speaking, there will be 2 ways you might try to train your agent. You might try to train it a policy directly, or you might try to train a value function, and then base your policy off the value function, which is what I've just been talking about. So let me focus on the second case. How would we actually go about learning this Q function? So we first of all maybe just initialize a random Q function, maybe it's zeros everywhere. In this case, the Q's everywhere will be 0 for every action, every state. and we start our worker out here, and we get it to play lots of rounds, and we somehow want it to learn the correct Q function. But imagine that we knew the Q function everywhere for every state in action, except for one state action there. And it'll be easy to get the last one because how should I write this? Yeah, maybe let me write it again. It'll be easy to get the last one because the return from the state that you ended up at, any of the states nearby, you know the Q function from there, and your return is just the reward you get from going there, and then the discounted reward, the return of being in that state. So there's a consistency condition, I guess, which is that the Q function for taking a certain action at a certain state is, and this is just a slight variation of what I wrote above, really, is the reward you get initially, and then Q function of being in that next state and taking the next action according to your policy. So here, A prime maps you to S prime. And A prime is chosen by pi. It's chosen by pi. This is called the Bellman equation. So it's actually, I mean, it's obviously a super simple equation, but it has a name because it's important for training. You can also write down a similar Bellman equation for the other types of value function, the V function or the A advantage function. It's because any step you take, you can then just think about the value of the state you're in next, or the advantage that you're in of the state you're in next. Maybe. Don't have a question? No. Is S. I'm starting in S. Maybe we should just draw this. We start in some state S, and then we take some action A to a different grid point, the S prime. And so we get the reward for doing this, and then a discounted reward for being in S prime and then taking the next action, A prime, that our policy wants us to take, whatever that is. So I don't have the next state. There would be some other state, but it's not, I don't need it. That should be, I think that should be correct. Any other questions about the value function or the Bellman equation? Yeah, so we could also have one for the value function. Which looks very similar. A prime with S is again S prime. Yeah, that's actually, I don't even need the last one. Yeah, that's fine. Okay. Say that again. A is an action. Yeah, I'm in. Maybe this is bad notation or something. Maybe that's why it's confusing. But I'm in the state S. Thank you. That was bad notation. And so this was wrong too, was it? Yeah, I see. Sorry. Maybe this was your question. I misunderstood. I'm sorry. There's no A prime in here, is there? Oh, until the end. That was a typo in my notes. Okay. Are there any questions now that it's correct? Okay. So I was saying that, if you knew the Q function for every possible, other state, you didn't know it in one state, you could just get it in this way through this sort of consistency equation. Now, in reality, of course, we don't know the Q function everywhere when we start. It's terrible everywhere. It's just 0 everywhere or something. We initialized it randomly. But what you might do is say, so this is a consistency equation. So we sort of want to impose it between two different Qs. If they're not consistent in this way, then they're not consistent with the rewards. So it's a good thing to want to impose, but if we actually impose it completely and the other Q functions aren't correct, Q values aren't correct, then we'll just like oscillate randomly and it'll be nonsense. What you might try to do is instead update your Q value a little bit. You might say, keep the same values as before, but update by a little bit alpha, where alpha is called a learning rate, times the difference between the right-hand side of the Bellman equation the right-hand side of the Bellman equation and the left-hand side of the Bellman equation. This would be zero if your Q function, if your Q for this state in action were correct. If it's not correct, and if this other Q were correct as well. If it's not, then you'll create some small update. The alpha might be like 0.1 or something. When we do an example in a second, I think it's 0.2 or something like that. Say that again? You're doing this for all the Qs, yeah. Yeah, see, the hope is that as you change this, as you make these tiny updates on every little state in action, that stuff will converge to the, I mean, if it does converge, it will certainly be at the correct one, because that's when it stops. But will it actually converge? I don't know, I'm not sure what the guarantees are. I mean, reinforcement learning is classically unstable. It's really easy to have instabilities in the problem. So I think, for example, we're going to implement this in a second. I think if you change your hyperparameters, you know, if you don't tune your hyperparameters in kind of a sensible way, then I think this will fail. So yeah, it's a classic problem in reinforcement learning that actually things are quite unstable. Okay. So is there any questions about this, about updating your Q function with this sort of consistency condition, the Bellman equation? And okay, maybe it's not guaranteed that this works, but is it kind of clear maybe why it will slowly bring you to a consistent Q function, which is actually consistent with the rewards? Okay. Okay, let me say one more thing. Good, okay. The way I actually do this update, right, is I go to these, I mean, how do I actually learn? How do I actually do this? How do I actually learn what these differences are? I have to step through the actions and get the rewards and see, was my Q function correct or was it not correct? I have to actually step through the different states and get these rewards. I have to find out what the rewards are so that I can actually impose this equation as I step around. How do we do that? I mean, currently we're following a policy, right? We're following this policy pi, and that's how we're stepping between states. And that's then the rewards we're going to find are just the rewards, the actions that we take at the states we go to. If we have some like terrible policy like we're here, and we just like, you know, keep bumping into the wall or whatever, we're never going to explore these other states and get all the rewards and actually update our Q function sensibly. So you definitely don't want to just follow the policy and only use the states you visit and the actions you take to update the Q function. The standard thing that you do is you build in some aspect of randomness, which is that you should follow the policy most of the time, but then sometimes you should just do something different. So this is a classic problem in reinforcement learning called exploration versus exploitation. So the exploration is when you go and look at new states to try to find out what's there. You try to do new actions for new states, try to figure out what's there. Exploitation is where you follow the best policy because you're trying to exploit your knowledge the best you can. So when you're done, when you've trained your agent, you want to go full exploitation. You just want to follow the best policy that you know. But early on, you want to explore. So a classic way to encompass that randomness is to use what's called an epsilon greedy policy. So what you do is you take the best action 1 minus epsilon of the time, and then you take some other random action epsilon of the time. Maybe epsilon is like 0.1 or something. And you might decrease this as you train, as you play. Because initially you want to be exploring and trying to find out the best, you know, trying to look at all the paths, but later on you want to focus in on the better paths and learn about them. You might slowly reduce this down. And this will happen actually in the code that we look at in a second. Okay. So if you do this, if you update your Q, if you walk around, you update your Q function with these little learning rate, and in particular, the way you explore is with an epsilon greedy policy. This is maybe one of the simplest reinforcement learning algorithms, and it's called the SASA algorithm, which is an acronym because what the information you need is state, action, reward, state, action. SASA. Yeah. So let's have a look at actually implementing this for our grid world problem. Sorry? This policy is stochastic, yeah. We've built some randomness into it, yeah. That's right. So hopefully you guys, like if you leave Google Colab on too long, it will like disconnect you. Hopefully that hasn't happened. You can still run things. Although if that has happened, I guess go up to the top and run those packages again because you'll need them in a second. But let's have a look at the code, some code that actually implements this SASA algorithm, so you can see how you might do it. So we're still working with that grid world, same map, let's run that so mine doesn't disconnect. Same seed, so it's exactly this maze. First thing we do is just initialize a Q table to 0. This just goes through and sets every single Q value to 0. We set a discount factor, 0.9, a learning rate, 0.2. P is just going to keep track of how long we've been training so that we can adjust epsilon as we go. Okay, so the number of training episodes we use is 6,000 or 6,001. And then as we go through an episode, we basically this is first finding some initial possible move. And then, well, if we haven't finished yet, we do the following. So we take steps, and each time we get a little reward, we learn what the next state is, we figure out if we finished or not. And then the next action here, this is getting the best action. So this would be just a purely greedy policy if we just did this, if we just followed the best action every single time. But instead of that, we're going to add, we add a little bit of randomness, which is this epsilon here is choosing a random action. It's choosing a random action following epsilon greedy policy with some non-zero epsilon. And then we just update our Q function, our Q table. So this is just exactly what I have on the board. We're updating our Q function to have this little piece of the difference in the Bellman equation. Yeah. Okay, so that's actually all this for loop is doing. We update it one last time, and then when we're done that, it's trained hopefully to do something sensible. And what this part of the code is doing is it's just going to now say follow that policy, epsilon equals 0, follow the greedy policy, see how you do. So this should, if you run this as well, you should find that this agent can now solve the grid world in 8 steps, which is the shortest number. 1, 2, 3, 4, 5, 7, 8. So it's learned how to solve this maze. Okay, are there any questions about SASA algorithm, the code that implements it? Yeah. Okay, good. All right, so that was a super, well, in some sense, a very simple reinforcement learning algorithm. It's not going to be powerful enough to solve more complicated problems. And one reason is because if we don't have discrete spaces, we don't even have a Q table at all. We're going to have continuous state space, continuous action space. You don't have a Q table. Even if it was discrete, but the Q table got huge, this would become a really computationally infeasible algorithm. So there's a load of reasons why this isn't going to work in more complicated cases. Actually, there's one last thing I wanted to say very quickly, which is this kind of thing is what's called model-free reinforcement learning. There's also model-based reinforcement learning, which is where your agent also has some internal representation of the environment that it's traversing. And it can like practice against itself or like figure out if I do this move, what's going to happen? Maybe this will happen. Something like AlphaGo uses to some degree a model-based version, has a picture in its head of how Go works, game of Go. But this obviously doesn't. The only things it ever finds out from the environment, it finds out by just moving around, by trial and error. Okay. Good. All right. So let's look at a more complicated environment which actually needs a more complicated algorithm. And then let's look at a more complicated algorithm. So Hopefully your guys' notebooks are still running. If you come to this point of the notebook, so we're going to look at a one of these OpenAI gym environments, which is this lunar lander one that I showed at the top. So we can click through and have a look at it. So I had a little GIF at the top. This is similar. So here there's this little lunar lander, and we're trying to make it land inside. There's no flagpoles here. There should be flagpoles, but this guy's trying to land inside this little like spot in the middle. And initially it just like falls, or it has some random momentum, and it just crashes. The action space is you can do nothing. You can fire the left engine, fire the like main thruster to push you up, and fire this right orientation. I think that's like a tilting. The left and the right like tilts your guy. That's why we have a discrete 4 action space. The observation space is where our guy is, x and y. These are relative to the point where we want to land it. The point where you want to land is like 0, 0. And then its linear velocity, angle that it's at the moment, its angular velocity. And there's these 2 booleans that tell you whether the legs have touched the ground or not. And it's trying to land in the center slowly so it doesn't like blow up. So that's why the observation space is 8, because there are 8 things. The way you can build this with OpenAI Gym is you just say gym.make lunar lander v2. There's a bunch of other environments. We're going to look at another one in just a second, but here's this lunar lander. There's a whole bunch. Okay. Yeah, and it terminates if it lands, which is great, or it crashes, or it flies out of the screen. Okay, so because this is a standard environment, we can really easily work with it in. So I said we were going to use this library of reinforcement learning algorithms called stable baselines. And in particular, we'll pick from this library to use this algorithm called DQN. So I talked to you about learning a Q function in a simple way with the SARSA algorithm. And I said that gets infeasible. Something you might try to do once that's become infeasible is model a Q function with a neural network. So your neural network will take in state and action, or let's say it takes in a state and an action and tries to predict the Q value. And then as you explore, you get information which you then train this network on, and it tries to approximate a Q function. The DQN is kind of one of the classic early algorithms. In particular, actually, this neural network, it's a convolutional neural network, and it takes in the pixels of the game you're playing, and it learns how to play based on that. So here's the paper that introduces DQN. It tries to play all these Atari games. It takes in a series of frames, like 4 frames or something, one after another, from the game, and then passes that through this neural network, and then spits out, what do I think that Q function is. This paper is 10 years old, actually, but already this was able to do better than humans on certain games like Pong and Enduro and these other games. I don't know what Enduro is. Okay, but if you want, you can have a look at this paper. But the basic point is it's just only a Q function, but it's doing it in a more sophisticated way. Okay, so we grab that from stable baselines, which I imported it above, and then we can just say DQN, and then we're going to pass it the environment we want to work with. Because this is a standard environment, we can just plug it in like that. MLP policy actually means that the network is a multi-layer perceptron rather than convolutional layer. So it's just like linear maps, fully connected activation functions. It's not a convolutional network, which would perform better, but you can change this around if you want. If you click through here, you'll see these different, there's a CNN policy. Okay, but if you want to run this yourself, you can set up this model, which is like ready to train on this environment. Here we create just a separate environment to evaluate how it's doing. You can have a look at this code yourself, but here we just evaluate this completely untrained agent. It does terribly. This is like the mean. In this environment, roughly plus 200 is like a good reward, minus 400 is bad. So you can train it. Here I'm training it for 10,000 steps. So the syntax is really simple because, like I say, it's a standard environment and a standard algorithm. So I can train it. You can watch it train. I'm doing it for 10,000 time steps, and it's done. And now we can check how well this guy performs. It's still not very good, actually. 10,000 is nowhere near enough. So you can try running it for 100,000 yourself and see if that's better. So we try to train it, and then we look at this trained guy, and we can you can save a little GIF of how it's performing. So this code here saves a little GIF, and it will save it in this files folder on the left, which you can open up by clicking on this little folder. And when it's done, I've already got one because I ran the whole thing. But when this is done, it will pop up on the left, and you can have a look. And this guy's trained terribly, obviously, at the moment. But yeah, so nowhere near enough time, so it will just crash. But if you train it for longer, you should be able to get this guy performing well. You could also try out using the convolutional neural network if you like. I actually didn't try that. And then, yeah, so have a play around with that for 5 minutes and see if you can see what kind of performance you can get. Okay, well, so hopefully you managed to train that to do certainly better than it was doing. Actually, mine's taking a little while. 100,000. Yeah, 100,000. Yeah, okay, maybe it takes like 3 minutes. Maybe you can get much better performance by training it for less time with a convolutional network, for example. I would imagine maybe you can. Can't fix. Oh, learning rate. I'm not sure. I haven't looked. You have to see the document. Yeah, sorry. Yeah, I haven't looked. I'd have to check. So hopefully this. Okay. Yes. If you train for 100,000 steps, it will probably be sort of decent. Maybe this was kind of a slightly bad run. But yeah, after 100,000, it does pretty well. Maybe you can train it for longer. Maybe you can train it with a convolutional setting. Okay, so maybe you've played around with that. You can have a look at some other environments and algorithms if you want to. For example, like I said, there's a bunch of other environments in Gym. You can have a look at this cart pole environment, where the idea here is this guy can move this little block around, the agent can move this block left and right, and it's trying to keep this stick from falling over. If the stick gets to like 12 degrees or something, it already cuts off because it knows it's going to fall. But yeah, basically the same syntax as above, but you can use this A2C agent, this is a different environment, cart pole v1, same stuff. You can save a little GIF, see how it goes. I think after like 10,000, maybe it's decent after 10,000. It does okay. Okay, but yeah, we got through that a little bit quicker. I mean, that's everything I want to talk about. You guys can just play around maybe with the environments as you like, or have a look at the other algorithms or whatever you want to do. Oh, thanks. Or if you have any questions, put your hand up and I can come around and. So obviously we didn't really get into the details of any of these more complicated algorithms. I just said, this is one of the better ones and you can use it. I guess reinforcement learning in general is kind of, it's a big field and it's kind of obscure, and some of these algorithms are quite hard to, might be hard to understand, so we can't really go through one in detail, but if you're interested, you can definitely, look up these algorithms, look up the papers that they came from, and find explainers. About? Sorry, I stood in here. Oh yeah, so A2C is an actor-critic model. That's right. So yeah, I mean, it learns. I think it learns a policy rather than a value function. But yeah, if you want to learn about it, I'd look it up. I'm not really an expert on it at all. Yeah, there's A2C. There's also A3C, which is related. Yeah, so I'd check out the paper or check out some other explainers. So by the way, you can also, if you want, you can look up the code for these environments. They're not hidden from you or anything. Frozen Lake is one of these environments. Let me just bring it up actually. Where is it? It's not there. Okay, yeah, so you can Google these environments if you want, and you can have a look at the code. And so if you're trying to say write your own environment that you want to couple with, that you want to run one of these reinforcement learning algorithms on, then if you write it in the same with the same methods, method meaning like dot step, dot reset, this kind of thing, as one of these like gym environments, then you'll see that you can just couple it in the same way to these algorithms. You should be returning the same stuff from your step as these OpenAI gym environments do. So this one is called Frozen Lake. It's like a grid world. It's just the same as this, but it's a frozen lake. You can fall in the water. So it has the same sort of setup, left down, right up. It will have its own. Often a lot of this is just for like rendering the world, like visualizing it. So it's not. You can just get past that stuff. But it's setting up an observation space and action space. So this is how you should do it if you want your environment to work with this, with say stable baselines algorithms. This is rendering stuff. This is all images stuff, not important. As a step function, you don't necessarily need to understand how it's doing everything, but as long as you're giving the same kinds of returns, this is done in some very like efficient, they're coding it in an efficient way, so you don't need to understand exactly, but as long as you're giving the same kind of returns. In this case, I guess this is like the state, this is the reward. I'd have to check what these things are, but yeah. Yeah, sorry, maybe I should have looked at this so I could tell you exactly which returns to give. But if you look this up, you should be able to find out what step needs to return, what reset needs to do. And yeah, you can make your environment have the same methods by making it inherit from gym.env like this. Yeah, you can take a look at this. Maybe Frozen Lake is the simplest, I'm not sure. Maybe the simple ones. I think Frozen Lake might be the simplest. Okay, and I mean, there's a tutorial for making your own environment on here, so you could definitely. Yeah, and it's for making a grid world actually, which is nice. Yeah, so yeah, if you're interested, maybe take a look at that. That's probably a good place to look. Okay. Yeah, I mean, I was done like 10 minutes ago. Yeah.